Hello, welcome back. So now we want to look at analytic and numerical methods. Right, so analytic method is interested in solving equations, solving for finding symbolic solutions, and then the numerical method focused in finding the numerical values. So if you consider a general equation of a polynomial, which is y is equals to a0 plus a1 x to the power 1, a2 x to the power 2, a3 x to the power 3 up until a n x to the power n. This is a polynomial in terms of n, degree n. So if n is equals to 1, you have got an equation of a line which can be analytically solved by making x the subject of the formula. So satisfy yourself that if you make x the subject of the formula for the first order polynomial, you get y x is equals to y minus a naught minus a1. For n is equals to 2, you get a quadratic equation. So with quadratic equation, we have different types of methods that we can use to solve this one. First, we have the quadratic formula. So we can use the quadratic formula to find two values of x. We can use factorization. We can use difference of two squares. We can also use what we call the graphical method to find the solution. So that's how we can solve this one. Right. So if you consider models involving sets of linear equations, how do you solve for x for each of the n equations? So if you have got one equation with one variable, you need one equation to solve for that one variable. If you have got two variables in an equation, you need two equations. You can't solve for two variables with one equation. And then for three variables, for example, x1, x2, x3, you will need three variables to solve such an equation. This one is what we called simultaneous equation. So go back and revise how we used to solve the simultaneous equation. Also try to look for examples and solve these types of equations. Probably I'll suggest you use the method of substitution. Right, so if you consider a logistic equation for growth, population growth, it is a differential equation of the form dn dt, which is equals to Rn bracket k minus n over everything over n, where n is equals to n naught is the initial population and t is equals to 0. So R is the growth rate, n is the population size, t represents time, and k represents the carrying capacity of a certain space. So yeah, carrying capacity. So the equation models growth populations, whether it's a growth of human beings, mosquitoes, whether it's a concentration growth in terms of concentration cultures. So any growth can be modeled using this general logistic growth equation. And then as you can see that when k when n approaches k, this top part will reduce to 0. So it will be 1 times 0 over 1 or 0 over n, which is 0 times 0. So the differential equation will approach 0 when n is equals to k. Or you can alternatively substitute for k, you substitute by n, so n minus n over n, this will give you a 0, so this will approach 0. So the solution to the logistic growth equation can be solved using mathematical software. This is the solution. This is the analytic solution. We are going to discuss how we solve these differential equations later, but this is just an example to show you that we can come up with an analytic solution, and use analytic solutions always give us the behavior of the equation, or the dynamics, or the changes in the population. For example, when t is equals to 0, we can observe our initial population, and when t approaches infinity, our population approaches k. Only this can be observed through this analytic solution. So when t approaches infinity, when t becomes very large, so if an exponent, a negative exponent approaching very large numbers, you can try to say e to the power minus 10 and see that you get a very small number. So eventually this whole term will collapse because it will approach 0, such that you remain with k over n to the 0 over n to the 0. So the initial populations will cancel. That's why we are saying nt will approach k, which is the carrying capacity. So these solutions can be analyzed in terms of behavior, analytical. And then the numerical solution, if we sketch or plot the logistic growth, it will give us something like this, where the population will start increasing up until it reaches a limit, which is the carrying capacity of that space. So for a numerical solution, you also need some numerical values to punch in, or to come up with a numerical solution. So why do we need differential equations? So consider a lake with a volume of 3 times 10 to the power 3 cubic meters and a stream flow into the lake at this rate. Assume that the outlet stream balances the inflow with negligible evaporation, so the lake volume remains nearly constant, at least on average over several years. Alright, so this question gives us an idea why we need differential equations. So we need differential equation because most of the phenomena in physical world, we deal with the rates, we deal with proportions, we deal with the rates of change, the change of flow, the flow of this over this, that's the rate. So whenever we want to look into the rate of change of deforestation with respect to time, change of rainfall patterns, maybe we are looking into climate change, so the change of the rainfall or climate or radiation. So as long as you want to look into the rates and changes of certain environments, or if you want to observe change, this is where the differential equation come in. They are good in modeling or representing changing variables. So just go through this homework and then try to come up with just simple equations that represent these following questions. Okay, thank you.